students, welcome back to another lecture in our course Environmental Modeling and Simulation. Today I am going to give you examples of 2D linear systems, and we are going to solve them to give you an idea of how to approach 2D linear problems analytically as well as graphically. In graphical approach, we also like to use both a little bit of the analytical approach, but we do not try to find an analytical solution. The first system that we are going to solve is this system, dx by dt, which is our first variable x is equal to x plus y is our second variable, and dy by dt is equal to 4x minus 2y. It is a classic textbook example, but it is very helpful to demonstrate the behavior of saddle node. So, here we can write A is equal to 1, 1, 4 minus 2. So, if you remember, the first step is to find a fixed point, which in this case we know will be 0, 0, which is the center of our coordinate axis in the phase portrait. So, now we are going to find the eigenvalues, and we need to do that whether we are using analytical approach or graphical approach. So, this is our characteristic equation. So, let us write it down. Okay, this is going to be a very easy problem to solve. You can factorize it simply. So, we have two values, lambda 1 let us say is equal to 2 and lambda 2 is equal to minus 3. Notice right here as we calculate the eigenvalues, we know that this is going to be a saddle node because one of the eigenvalue is positive. So, in one eigenvector direction, the flow of the trajectories will be away from the fixed point 0, 0, and in the eigenvector corresponding to lambda 2, the flow will be towards the fixed point. So, we are going to get a saddle node. Now, let us find out the eigenvectors. To find the eigenvectors, we are going to do this. So, here let us again write our A minus I lambda. So, let us put in the value 2, which is corresponding to lambda 1 first. Okay. So, we substitute the value of lambda 1 here in this matrix. So, here you will get so what we are going to get, you look at this system, it will give you a non-trivial solution. So, the non-trivial solution is basically V1 by V2 is equal to 1 by 1. Okay. Now, let us find out the eigenvector for lambda 2 is equal to minus 3. So, let us erase this part and let us find out the eigenvector corresponding to lambda 2. So, corresponding to lambda 1 equal to 2, our eigenvector has a non-trivial solution where V1 by V2 is equal to 1 by 1. Now, for lambda 2 is equal to minus 3, the system will look like this. Again, this system is going to give us a non-trivial solution where V1 by V2 Again, the system is going to give us a non-trivial solution where 4V1 plus V2 will be equal to 0. So, basically V1 by V2 is equal to minus 1 by 4. So, these are our two non-trivial eigenvectors. Now, let us plot them. Let us make a phase portrait using graphical approach. So, using the graphical approach, Let's do analytical approach first because it's more tiresome. So this is our second eigenvector, this is our first eigenvector. Let's use analytical approach first to understand how tiresome it can get, and then we'll use the qualitative approach, the graphical approach, to understand how accessible it can make and how easy it can be to understand how the system behaves. Alright, we have the eigenvalues, we have the eigenvector, and let's say the initial point is given to us x naught y naught is equal to 2 minus 3. So let's say the x naught y naught, the initial value is given to us as 2 and minus 3, okay. So we know that our solution xt is equal to C1 E lambda 1 t V1 plus C2 E lambda 2 t V2. So we are going to substitute eigenvalues, eigenvector in this, and then for time t equal to 0 we are going to substitute this value and find our solution. So basically x with time varies so. So basically x and y with time will vary so. Which we can write like this, C1. Now what is lambda 1? 2t. Corresponding to lambda 1, our eigenvector was 1, 1. Second eigenvalue is minus 3. And corresponding to eigenvalue minus 3, our eigenvector is minus 1 by 4. Okay, so this is our solution, and we can write it like so. Now let's substitute the initial value, which is 2 minus 3. Okay, so at time t equal to 0, x is 2 and y is minus 3. Now we can solve these two together. So C2 is equal to minus 1, substitute it here, and we get C1 is equal to 1, right? So now we know our values of C1 and C2, we can substitute it in these equations and we get the analytical solution for x and y. So at any given time, we know exactly how x is changing and how y is changing. But looking at this system, you cannot very clearly understand how the system is actually behaving. Like the clarity of understanding will be missing here unless you plot it using a software. The graphical approach, the geometrical approach will make it slightly easier for us. So let's use the graphical approach. So using geometrical approach, we are going to make our phase portrait first. So remember, in 2D phase portrait, the axes will have our variables. So here we have x, here we have y. First, let's find the fixed point. The fixed point we know is 0, 0. Next, let's find the eigenvalues. Corresponding to eigenvalues, we need our eigenvectors. So eigenvector corresponding to eigenvalue 1 is 1. Eigenvector corresponding to eigenvalue 1 is eigenvector corresponding to eigenvalue 2 is given by this. Hold on, minus 1, 4, perfect. Okay, so let's plot eigenvector 1 first. It is 1, 1. So this is the trick here. Move 1 unit in x direction and 1 unit in y direction, and then connect these two. This is your eigenvector 1. And the corresponding lambda is 2. Now let's draw eigenvector 2. Move minus 1 unit in x direction and then plus 4 units in y direction, and then join these two. This is your eigenvector 2, corresponding to lambda 2 is equal to minus 3. Okay. In the direction given by v1, eigenvector 1, lambda is positive, so the flow is away from the fixed point. In the direction of eigenvector v2, lambda 2 is negative, so the flow is towards the fixed point. We already know this is a saddle node, the fixed point is a saddle node because the sign of lambda 1 and lambda 2 are different from each other. And we have already gone through how the flow happens around the saddle node. So, this is what is to be expected. Now, if I know my initial values, if I know my initial condition and I know where the initial condition is in this graph, I can already understand what will be the qualitative fate of the trajectory, where the trajectory will end. Will it end here in the first quadrant pointing towards the infinity, or in the fourth quadrant, or will it end up in the fixed point? Okay. Now what I want to do is I want to take another example, a very simple example, and walk you through different kinds of shapes, different kinds of trajectories that we can expect around a fixed point in 2D linear system. So let's take a very simple example where we have dx by dt varying as ax and dy by dt varying as minus y. Okay. Now we can write, if you are trying to solve this analytically or graphically, either way, we need to write the characteristic equation first. So let's write it with the right notation. So our characteristic equation is given by this. So this is a simple quadratic equation that we can solve using the Sridharacharya rule. So we have lambda is equal to we will get lambda 1, lambda 2, this will become a plus 1 whole square by 2. So we get a and minus 1. So let's say a is lambda 1 and minus 1 is lambda 2. So the next step now is to find the corresponding eigenvectors. Now to find the corresponding eigenvectors, we need to do this. So for lambda 1 is equal to a, again we get a system where the only meaningful solution is that V2 is equal to 0 corresponding to lambda 1 is equal to a. Similarly, for lambda 2 is equal to minus 1, we will get V1 is equal to 0, which is actually very easy to interpret. When V2 is equal to 0, which it means that corresponding to a, the eigenvector is our x-axis. And when V1 is equal to 0, it means corresponding to eigenvalue 2, the eigenvector is basically y-axis. So let's plot this now, the phase portrait. So this is our phase portrait, here x is changing, here y is changing. One eigenvector, I am going to use a different color. So one eigenvector is here and another eigenvector is here. The corresponding eigenvalues, lambda 1 is equal to a for x axis, lambda 2 is equal to -1 for y axis. So, here the eigenvalue is -1 and here the eigenvalue is a. Alrighty. Now, what we are going to do is we are going to vary the value of a and we are going to see how the trajectories behave differently around the fixed point 0, 0. The fixed point here is 0, 0, alright. So, let us start with a less than -1. So, let us say we are now pay special attention here students. Let us say we are starting here. This is our initial x naught, y naught. A is less than -1. Now, the movement for this particular fixed point will happen, as I mentioned earlier in the previous lecture, in the direction of the fixed points, direction of the eigenvectors. So, one eigenvector is here, another eigenvector is in this direction. In the eigenvector that is parallel to y-axis, the flow, the growth rate will be -1. So, the movement is towards the fixed point, and the unit, the magnitude of the growth rate is 1. In the eigenvector that is parallel to the x-axis, the growth rate is a, which is negative. So, again the movement will be towards the fixed point 0, 0, but the magnitude would be a. Notice a is bigger than -1. So, basically this point that is starting here at x naught, y naught, is going to get bigger growth, in this case decline in x direction than in y. So, it will reduce rapidly in the x direction as it slowly reduces in y direction. So, what will happen is that as this point, phase point approaches the fixed point, it will eventually become tangential to y. Similarly, if it is starting here, the decrease in x direction will be much faster than the decrease in y direction, because a is less than -1 and the decrease in y is governed by -1, right. These are your eigenvalues. So, again we will see that the decline in x axis will be very fast, and as this phase point approaches fixed point, it will start becoming tangential to y axis. Let us see what happens in second quadrant. So, let us start from here, right, close to y axis. Once again, in this direction the magnitude of change is governed by a, the magnitude of a. In this direction the magnitude of change is governed by eigenvalue 1, -1. So, what will happen is we will see the decrease, because a is less than -1, the decrease in x direction will be much rapid compared to the decrease in y. So, again as this phase point approaches fixed point, approaches the fixed point, we will see that the trajectory becomes parallel to y axis. Now, notice one thing that I skipped over. A is less than -1, which is equal to one of the lambda values, and the other lambda value is also -1. So, both lambda values, lambda 1 and lambda 2, are less than 0. So, we are dealing with a stable node. So, all trajectories will point towards a fixed point. Same thing here. The flow lines will become parallel to y axis, and we will see similar behavior in the third quadrant and in the fourth quadrant. So, when a is less than -1, what we see is a behavior like so. All the approaching lines become parallel, to y axis. In fact, this brings me to a very important point. What we notice is that the trajectories tend to become parallel to the eigenvector, which corresponds to slower eigenvalue, slower eigenmovement. So, let us say we have two eigenvectors v1 and v2, right. The flow here is lambda 1, the corresponding eigenvalue is lambda 1, the corresponding eigenvalue is lambda 2. So, let us say lambda 1 is less than lambda 2 is less than 0, alright. Now, lambda 1 is less than lambda 2 less than 0, which means lambda 1 magnitude is going to be bigger than magnitude of lambda 2. So, v2 is going to be the slower eigenvector, and the trajectories will become tangential to v2. Okay, let us take another example now. So, this is a case of stable node, and the trajectories are getting tangential to the slower eigenvector as they approach the fixed point. Now, what happens? When a is equal to -1? So, the flow in this direction is governed by lambda equal to -1. The flow in this direction is also governed by lambda is equal to -1, right. So, what we will see is in this particular situation when both lambda values are constant, what we see is that let us say this is our starting point x naught y naught. What we notice is that we get straight lines. Now, notice again here both eigenvalues are less than 0. So, again we are dealing with a stable node, but we are dealing with a stable node, but it is very interesting that your trajectories look like straight lines. Such a node is also known as star node. It is a stable node which is a star node. Okay. Now, let us look at another case where A is greater than -1 but still less than 0. So, the eigenvalue corresponding to the movement in this direction is given by A, which is between 0 and -1. The eigenvalue corresponding to this direction, movement in this direction, is -1. So, now the movement is faster in the direction of y axis corresponding to relative to the movement in direction of x axis. So, what we will see is that the trajectories that come, they will become parallel tangential to x axis as they approach the fixed point. Because the movement, the change, the flow will be faster in y direction than x. So, in all quadrants, this is how we will see the behavior. Again, we are dealing with a stable node, but it looks very different from this stable node. Okay, now let us change the value of A further. Let us make A equal to 0. So, now A is equal to 0. So, the eigenvalue corresponding to movement in x direction is 0. The eigenvalue corresponding to movement in y direction is still -1. Now, what happens when eigenvalue is 0? Remember, I told you eigenvalue gives us an idea of movement in a particular direction, because our net solution is basically C1 E lambda 1 T V1 plus C2 E lambda 2 T V2. So, in the direction of V1, lambda 1 is governing the growth. In direction of V2, lambda 2 is governing the growth. So, if in this direction, the direction that is moving in x axis that is pointing, that is coincident with x axis, if your lambda is equal to 0, what happens is that there is no movement in the eigenvector direction. So, the only movement we will see is in the direction of eigenvector corresponding to lambda is equal to -1. So, let us say this is my starting value x naught y naught. The movement in the direction of y axis is governed by lambda value is equal to -1. The movement in direction of x axis is governed by lambda equal to 0. So, no movement in the direction of x axis, no movement here. So, in this case, how will the trajectories look like? The trajectories will simply look like this. Let us say this is our starting point. Let us say this is the starting point. No movement in the direction of x axis. Notice something very particular, very peculiar here. In this case, all the movement that is happening in y direction, which means if our initial point is on x axis, it will not move, right. So, the entire line that coincides with x axis in this particular case when A is equal to 0 becomes line of fixed points. So, if you ever encounter such a situation in a model and I ask you the question, how many fixed points are there, what kind of fixed points they are, all you need to say, well, we have unlimited number of fixed points, we have a line of fixed points. It is also possible that we have a situation where the entire face plane, this is face plane where we are drawing the face portrait, the entire face plane is basically a plane of fixed point, which means there is no movement, there is no change in the variables happening with time. In this case, y is still changing, but x remains constant, and what we have is a line of fixed points. Okay, let us make A positive and see how the movement will happen then. So now A is greater than 0, A is positive. So fun, this is fun, you already know what's happening. Let's say I forget what were the corresponding numbers we gave, but okay, so lambda 1 is A, perfect. So lambda 1 is A, so lambda 1 is A, lambda 2 is -1, corresponding to vector 1, corresponding to vector eigenvector 2. Now notice, in the direction corresponding to eigenvector V2, we are still seeing a decay. So the movement will be towards the fixed point 0, 0. In the direction corresponding to eigenvector V1, now eigenvalue is a positive number, A is positive. So we will see growth instead of decay. So what are we dealing with here, dear students? I hope you have guessed it correct. We are dealing with a saddle node. By now, you must know how a saddle node behaves. Okay, students, this is all for today's lecture. And in the next lecture, we will continue and try to understand how trajectories behave in 2D space. And we will look into more examples that make it more clear for you. Thank you.